Hi, I'm Henri Drake. I'm a postdoc at Princeton University. Today, I'm happy to talk about some of my work I've been doing with my PhD advisor, Rafael Ferrari from MIT, who we joined program, and Shadro Ruan, also at MIT. So I'm going to talk about diapycnal motion, diffusion, and shear dispersion of tracers in the ocean. That was just a movie of the process in the background. And so the context I want to talk about this is the fact that in the deep ocean, observations show that ocean mixing is strongly bottom enhanced over rough topography. So if we think about a parcel of water like this, that is experiencing this bottom enhanced turbulent mixing, shown or illustrated here by the turbulent buoyancy flux, we can think about how that affects a parcel by thinking about the buoyancy equation. And so the material derivative of buoyancy is just going to be equal to the divergence of the turbulent buoyancy flux, where here we're thinking about buoyancy as being filtered over scales larger than the mixing process, and thus the diffusivity here representing an effective turbulent diffusivity many times larger than its molecular value. And so if we think about what this bottom enhanced mixing is going to do, it's going to cause this parcel to mix more with the denser water below than with the lighter water above. And thus this turbulent buoyancy flux will diverge, leading to a negative buoyancy velocity. And so we're going to use this omega as a shorthand for the turbulent flux divergence throughout. So if we think about what happens sort of on average in the ocean, we can't just think about one isolated water parcel. We have to think about what happens along an entire buoyancy surface, for example. So this is the approach that's taken in water mass transformation analysis. And so in particular, although you're going to have this downwelling in the interior, if you think about what happens right at the bottom of the ocean, this parcel is still going to mix very strongly with the lighter waters above it. But at the bottom of the parcel, you have the seafloor, which is either going to be insulating or perhaps there's a weak geothermal heat flux. In any case, this parcel is going to converge buoyancy due to mixing and thus upwell. And so the idea here is that to balance the downwelling or formation of bottom waters around Antarctica, you have to upwell water somewhere. And so the thought is that mostly happens in these rough bottom enhanced mixing bottom boundary layers. So the point of this talk is to think about how we might be able to observe this process, in particular using tracer release experiments to directly infer the diffusivity experienced by the tracer or the buoyancy velocity directly. And then also, think about how these bottom mixing layer circulations, this downwelling and upwelling dipole, how does that affect tracer transport more generally? And so we might expect that picture to look something like this, where you have sinking in the interior, but also some diffusion. And then at the bottom, you have this tracer rapidly upwelling. So the approach we're going to take quantitatively is this tracer moment method pioneered by Ruan and Ferrari in a recent JPO paper. So we'll start with just the buoyancy equation I've shown before, as well as a tracer advection diffusion equation. And so the idea is to cross multiply these. So now you have an evolution equation for their product. And if we integrate that over some large volume and normalize by the total tracer mass, that actually gives us an evolution equation for the tracer weighted average buoyancy of the tracer in this case. And so if we reorganize this equation and we apply boundary conditions at the insulating seafloor, and also if we integrate sort of horizontally over a large enough volume that the tracer concentration goes to zero, then we find that the average buoyancy of the tracer evolves like twice the average buoyancy flux convergence. So using the shorthand, this is just twice the average buoyancy velocity, omega. And you can also do this same process for the second moment equation. You can find that in the paper. I won't go through that here. So the way that I'm going to diagnose these terms, I'm going to use this quasi-realistic simulation of the Brazil Basin tracer release experiment. This is showing you the topography of the region where we're on the flank of the mid-Atlantic ridge in the South Atlantic. You have the abyssal plains, these deep seafloors on the left, and then that sloping upward gently towards the crest of the mid-Atlantic ridge. And this flank is incised by this 1,000 meter deep fracture zone canyon. And so I'm going to align my domain with that canyon. And the reason I'm picking this particular canyon is because there was an actual tracer release experiment here by Ledwell et al. In the 90s. And also there were various other measurements like moorings and microstructure in this canyon as well. So in particular, I'm going to force this model with the observed microstructure measurements of the vertical diffusivity. So something that looks kind of like this, it's strongly bottom enhanced, exponentially so towards the bottom, based on the local height of the bottom. And I'm going to do 3 of these tracer release experiments. So one is the realistic release. I'm not going to talk about it here, but it's in the paper. And then one right at the height of the canyon crest, which is this gray line here. And then one right at the bottom of the canyon, which is the results I'll show today. And then I just want to point out that there's no explicit tidal or other forcing, just this imposed mixing. And then also that I'm using this linear equation of state. And so buoyancy and temperature in this case are proportional. And I'm just going to talk about temperature here and ignore salinity. It doesn't vary. So here's kind of the key result. We release this tracer at the bottom of the canyon here, and it upwells across these temperature surfaces, but also sort of towards the right up the canyon axis. And the red colors here show the cross canyon integral of the tracer concentration. And so the dark reds are very large values. So you can see that the tracer upwelled in the net. To see that a bit more clearly, you can integrate along these temperature surfaces, and you can see that at the initial release, the dotted lines here show a very constrained release point. And then over a 14-month period, the tracer is on average upwelling, and then it also seems to sort of spread on average in temperature space as we would expect for a diffusive process. I also want to point out here that there's also stirring in the horizontal or along Diapycnal surfaces, and that's by these submesoscale baroclinic eddies that populate the domain and feed off of these horizontal buoyancy gradients due to the mixing. So if we now diagnose this tracer moment equation from the simulation, we can look at how this upwelling happens a bit more quantitatively. And so here I've just divided by 2 so that the half of the temperature gain of the tracer is just driven by the average buoyancy velocity. So this is also sort of a way of, in practice, inferring the average buoyancy velocity in a region by measuring how a tracer upwells in temperature space. And so what that looks like here, the solid line is just showing this rapid upwelling that increases over the first 150 days and then decreases. And if we think about what's really going on here is that we can decompose this into the strictly upwelling component and the strictly downwelling component. And so what's happening is that right at the beginning, the tracer is all right at the bottom, very confined, and it's all completely upwelling. There's no downwelling of the tracer, but over time, some of it gets stirred into the interior where it starts to downwell. And that downwelling sort of grows over time such that the net upwelling is actually going to start decreasing over time as the upwelling stays roughly constant, but the downwelling part grows faster. If we think about the second moment equation, so this is telling you how the temperature variance of the tracer changes over time on average. And that actually has 2 terms. So one is this diffusion-like term. You can see it's proportional to the diffusivity. And then actually, if the diffusivity is uncorrelated with these temperature gradients, well, then those two cancel out, and you actually find that the temperature variance normalized by the gradient squared just goes like the diffusivity. And this is kind of a classic result from turbulence acting on tracers by Taylor in the 1920s. But the new thing here is that you also have this second term. And so this second term has to do with correlations between the local buoyancy velocity and the local temperature anomaly of the tracer relative to the tracer average. And so this is a kind of shear dispersion effect. It has to do with different parts of the cloud experiencing different diapycnal velocities. And so if we think about what's happening to the spreading of the tracer over time, we can see it by this solid red line. So the tracer at first is spreading pretty rapidly, and this is mostly due to this diffusion, the dashed lines here. But it's also enhanced by this shear dispersion effect. So the shear dispersion for the first 150 days is actually enhancing, amplifying the diffusion. But then after that, what's interesting is actually the shear dispersion term changes sign and becomes negative and is becoming increasingly strong and is suppressing the diffusion. And so it's causing the tracer to spread slower than you would expect just from diffusion alone. And then finally, in the last 100 days, the shear dispersion effect becomes so strong that it actually overwhelms the diffusion and causes the tracer to contract in temperature space in the net. And so this is very counterintuitive, which is that in this model, at some points, applying diffusion to a tracer can actually cause it to contract. So to try and understand this shear dispersion effect a bit more, I want to go through two sort of illustrative cases so that it's simplest to think about a tracer cloud, which basically is just two isolated particles of tracer that make up the cloud. And so if we use these delta functions in two different locations, we can actually evaluate this term analytically. And so the shear dispersion effect just becomes the product of the difference in buoyancy velocity of the two particles and the difference in temperature. And so to think about that, we can think about two scenarios. So one is where the warmer particle is upwelling. And so in this case, let's say it's at the boundary and it's upwelling really rapidly. And then the denser particle is downwelling slowly in the interior. So that is going to cause this tracer to stretch because the upwelling part is going to upwell faster, and the sort of denser part is going to downwell. Alternatively, we can think of this case where the warmer or more buoyant of the particles is downwelling in the interior, and the denser part is upwelling, say at the bottom. And so this is going to cause this contraction because the sort of already denser parts of the tracer are going to upwell, whereas the lighter parts are going to downwell, and it's going to contract it in temperature space. And I just want to point out that this is exactly what's going on in the simulation at the end of the simulation. And so here, if you think about this red cloud of tracer as just sort of having two major poles, you can think about this sort of tongue of tracer in the interior as being pretty warm and downwelling. And then this part at the boundary is denser and upwelling. And so that's actually going to cause this really strong contraction effect. So to summarize, we've presented these exact tracer-weighted buoyancy moment equations that relate tracer statistics to turbulent flow statistics. And the Diapycnal motion is driven directly by the average turbulent buoyancy flux divergence. That's the first moment equation, but that simple result kind of obscures the fact that some parts of the tracer might be upwelling really rapidly while other parts might be downwelling really rapidly. And so we can decompose that in this model. And then second, that if you go to the second moment, you find that the evolution of the variance or the Diapycnal spreading is actually driven by a combination of two terms. There's the straightforward Taylor diffusion, and then there's this additional Diapycnal shear dispersion term that arises only in heterogeneous turbulence or in the presence of a boundary. And in particular, while diffusion is positive definite, it always acts to spread a tracer. This shear dispersion effect can be of either sign and can even overwhelm the diffusion. And I want to encourage you, if you're interested, to read the paper itself and a companion paper on the dynamics of the flow on my website. There's preprints. And then happy to take questions either in the open session, the live session, or feel free to email me. And then also please stick around and check out the talks by Xiaozhou Ruan on the actual process that drives this bottom enhanced mixing. And then also Bethan, Win Katnack on these amazing observations where they released a dye and are observing this upwelling in practice. And thanks a lot.